All right, guys, so what we're looking at here from the 2013 exam is a problem that, although it looks like a polar equation problem, and it is a polar equation problem, strangely enough, this kind of morphs into a parametric equation problem as well. So it's got a little bit of both mixed in, just so you're aware. There's nothing overly difficult on this problem. Let's go ahead and jump in to make sure we understand what's going on. So I've got this graph. We've got the polar curves r equals 3. That is just the normal looking circle right there. And then r equals 4 minus 2 sine of theta, which is the sort of normal looking circle, but it kind of goes down further right there. And then it tells us that the curves intersect at theta equals pi sixths and 5 pi sixths. Remember, we always look at polar graphs moving around the circle. So where they cross is at pi sixths and 5 pi sixths. So not an awful lot of information given here. That's what they give us. Now, letter A says, let S be the shaded region inside of the graph. So what I want to do here to find that shaded region is I actually want to separate this into two separate things. I want to separate it into this circle, and that is 2/3 of a circle. And if you, I'm not going to go into too much why. You can figure it out. If it goes from pi 6 to 5 pi 6, that is a difference of 4 pi 6, which means I have 8 pi 6 left over for the rest of the circle. Again, I know that's kind of confusing. Anyway, for the area of that shaded region of the circle, it's going to be, since it's not a whole circle, but it's 2/3 of a circle, it's going to be 2/3 times pi times the radius squared, which is 3 squared. So that's the first part. And then I'm going to add this region right here. Well, in order to find that region, we're going to go from pi 6 to 5 pi over 6 of 1/2 times that radius function that they give us, the 4 minus 2 sine of theta, and then we square that. And when we put that into our calculator, you get 24.709 or 708, depending on how you typed it in. So that's your answer for letter A. Again, we have most of a circle here, and then we've got our area that we use between a polar graph and the origin for the second part. All right, the second one says a particle moves along the polar curve so that at time t seconds, theta equals t squared. Find the time for which the x-coordinate of the particle's position is equal to 1. So what we have to realize is we've got, okay, I've got an x-coordinate. Remember, x is equal to r times the cosine of theta. Well, my r in this case is 4 minus 2 sine of theta. So that's going to give me my x-coordinate. Then I'm going to multiply that by cosine of theta. But this doesn't want to know that. It doesn't want us to just set that equal to -1. It wants to know the time at which that's going to happen. So once I have this formula set up, I take my t squared and I put that in for both of the thetas here. I'm going to have 4 minus 2 sine of t squared times all of that multiplied by cosine of t squared. And I want to know when that's equal to -1. So I just graph this in y1 and y2, and I find out that those two graphs cross at 1.428 on the interval from 1 to 2. There are actually lots of other places they cross, but the place that I'm interested in between 1 and 2, I graph it on my calculator, is 1.428 or 1.427, depending on how you round. So that's your answer for letter B. Now, letter C, still talking about the same thing from part B, we want to find a position vector in terms of t. Well, we already found the x-coordinate, remember. The x-coordinate was, we had 4 minus sine of t squared multiplied by cosine of t squared. That was my x-coordinate. My y-coordinate is virtually identical. Remember, a y-coordinate in polar coordinates is r, which is my 4 minus sine of theta, but we're putting t squared in, multiplied by the sine of theta, which again is t squared. So what we have here, although it looks like it started off as a polar equation, we've kind of changed it into a parametric equation. Now that we've got our position vector, so we've got our x of t and our y of t, it also wants the velocity vector at time equals 1.5. Well, that's really easy. All we have to do is take the derivative of this and plug in 1.5, and our calculator does that. And when you do that, you get negative 8.072. Then we do the same thing for our y-coordinate. When I plug that into my calculator and I take the derivative at 1.5, I get negative 1.673. So this one on letter C, that's how we get both of those answers. Again, here's our position. Whoops. Here is our position vector right here. And then here is our velocity vector when we plug in 1.5. Hopefully all of that made sense. If you have any questions about this problem or any of the other problems, please let me know.